5 plus. So what we have here is 5 plus sum of 5 minus 1, which is 4, right? And then we are calling this again. So we have some 4, which is 4 plus some 3. So like that is recurring. As we see that it keeps calling itself. And then the base condition is where we stop. So where we stop at the case where x is 0. So if x is 0, we don't need to do anything again. We want to stop. So if you have a function, if you have a recursive function, you must have a base condition like where you need to stop. Else, like your function will just keep running forever. So that's basically it. Now, so this is an example of this is an example of a function that calls another function that calls another function. So if we look at the first function called A, so A returns hello plus the B function, right? B returns my plus C function, C returns friends. Now, I want to explain the call stack because we would need to have like a little bit of idea of what the call stack is to understand recursion. So this is a call stack. So I think, I'm not sure if we've covered stacks, but stack is basically a structure where you can only add to the top or take out from the top. So you say you have like a list of books, right? Or a container that holds something. You can like always pick out, you can only take out from the top or add to the top. So you can't take from the bottom. So when we are at this function, where we are calling a function, we have hello plus B, right? Plus B call, but we don't know what B returns, right? So we'll say, hold on, let's go and find what B is first, right? And then we go into B, which is here on line 7, right? So when we go into B returns my plus C call. So B doesn't know what C returns. So we'll say, okay, let's go into C to see what C is going to return. And then we go into C and we see that, oh, C just returns friends. So at this point, C doesn't call any other thing. So we can say C, like this is the base condition because we've gotten to the end of the call, like the calls that we are making. Now, at this point, we can now, so as you see, we are adding to the top, like we just keep adding to the top of the stack, right? Now we've gotten to the basic condition and we can now take out of the top of the stack. So we then say, okay, friends. So we now know that this C call is friends. So we say, okay, my friends. So B understands what the C call returns. So we just have my friends now. And then we pop up back to A. We go back to A, and then A now knows what B returns, which is my friends. So we now have like, we can now return the like everything basically. So I think I would stop here and see if there are any questions before I continue. Or I don't know. Do you take questions? I don't know.
I think they are super smart people, so they are following you. No, I don't have any questions. Everyone, yeah.
So,
okay, someone just dropped a question in the chat. They said, can you repeat the definition of base condition?
Okay. Before I repeat the definition of base condition, when people don't have questions, it's either of two things. So one is either everybody understands or nobody understands. So at least we have a question, so it means people are following. So base condition, access. Okay. Yeah. So the base condition, as I said, base condition is basically the point where you stop the recursive call, right? So you are no longer going to call the function itself. You're not going to call the function again by itself, right? So let's look at this example again, right? So this function sum, right? When you call this function, it is not going to stop until x is 0, right? So it will keep calling itself. So if you maybe recall sum with say 7, so at this point, at the first, so if you think in the terms of the call stack I showed in like just now, the first time we call the function is we have x as being 7, right? So we are not going to get into this if condition. We are going straight to this return, and then we're going to call sum again, right? So here we'll now have 6. We are not going here. We'll still keep calling and reducing x. So from 7 to 6 to 5 to 4 to 3 to 2 and then to 1 and then to 0. So when x gets to 0, we can now stop the recursive call. So if we don't have this if x is 0, what will happen is we'll get to -1, -2, -3, and till infinity. And even before then, the laptop will probably have crashed or whatever PC that the function is run on, right? So we always need to stop the recursion at a particular point, right? So that is what the base condition is. So the base condition basically ensures that our recursion doesn't keep running forever. I don't know if that answers your question. Okay, cool. So I think we probably now have like a little bit of understanding of what the call stack is.
Yeah, and somebody else, okay, I think she got it already. Because she was asking that does the base function means the last function called?
No. Okay, good. Okay, she has gotten it now.
Yeah.
So yeah, I think that's basically it. I don't want to go into the cons of recursion yet until maybe we have like 1 or 2 examples. So let me see if we can go into a bit of code. Second. Okay, let me stop sharing. Then if you have any questions, you can drop them in the chat. Okay, let me share my screen again. All right. I think I need to increase the size of this. So let's say we have a question to find. Okay, we've already done this, but like we already have this in the example, but let's do this again. So we need to find the sum of numbers from x, right? So given number x, find the sum of the positive sums of numbers from 0 to that number, right? So that's basically what we want to do. So we know that so if, for example, we are given 5, we know that what we need to do is we need to do 5 plus 4 plus 3 plus 2 plus 1 and maybe possibly plus 0, right? So when we see that, okay, this is the problem that we need to solve, right? So we think, is there a recurrence relation here? Is there something that we keep doing every time? So it seems there is something. What we are doing is we are adding 1 and we are subtracting 1 from the number. So if we have 5, right? At first we have 5. So what we do is subtract 1 from 5, which is 4, and then add it, right? So if we have 4, we subtract 1 from 4, we have 3, and then we add it. So we are doing two things, subtract 1 from the number and add, right? So subtract and add. Those are like the two things that we are doing, right? So we already have the recurrence relation. As we can see that, okay, we have 5. We started from 5. We subtract 1 from 5, and then we add it. So we have 4, and then we add it. So we have 4, subtract 1 from 4, we have 3, we add it. We have 3, subtract 1 from 3, we have 2, and then we add it. So we have, this is the recurrence relation, the subtraction and the addition. And then the base condition is where we stop, right? So we stop at 0, right? If we didn't have, if the question didn't say the sum of positive numbers, right, then maybe we can keep going to like -1, -2, and the rest. But the question basically says we stop at 0. So 0 means the base condition. 0 is basically the base condition. So we can now have a question, say, so we can now solve the question and say function sum is first giving a number. So we're giving a number x, and then we are supposed to subtract and then add. So we return x plus, so we need to subtract 1 from x, which is x minus 1, and then add it. So this, but we need to keep doing this. We just need to keep doing this. So we would call this thing again, the function again, because we need to do that. Like we need to continue doing that. All right. So this is basically the recurrence relation, and then we need to stop at the base condition. So if x, so the base condition is when we get to 0. So if x is equal to 0, then we need to stop. So at that point, we just return 0 to stop. So that's basically it. That's like it's like one of like the simplest questions with recursion. Now, how do you find a question, and how do you know that, oh, this question is a question that I can solve with recursion? So as we said, there are two things you need to find. We need to find the recurrent. We need to ensure that there's a recurrence relation, and then there's a base condition. If we can find these two things, we know that we have like a question that we can use recursion for. If we go to say lead code, for example, and we go to problems. So this is okay. This is like just one example. This is one example. So if we read this question basically implements power. So x raised to power n implements power xn, which calculates x raised to the power of n. That's x raised to power n. So we are given a function, and we are given a value x, and we're given another value n, right? So how do we solve this problem? And can we find a recurrence relation, and can we find a base condition? So let's find out. So let's have the question. So we have implement power x, which calculates x raised to power n. So what we can do is we already know what power means. We know that if we say 5 raised to power 3, it means 5 times 5 times 5 3 times, right? If we say 6 raised to power 7, it means we need to say, if we say 6 raised to power 7, then we are multiplying 6 7 times. So 6 times 6.
Hi, Ekene. So we have
Yes.
some questions on the group chat, on the chat.
Okay.
One is, can we return a recursive function?
Can you return?
Yeah, I don't know what they mean.
Okay, I'm trying to understand what you mean by return a recursive function. But so if so this function, right, sum is a recursive function because it keeps calling itself, right? And the return value here is x and the recursive function. So we are somehow returning the recursive function and we are summing a value and then the recursive function again. And that's what we are returning. But I don't really get your question. So another question is it efficient to use stack in a back of the recursion? Okay, I also don't understand this.
Sorry, I probably
Yeah,
didn't word it right. Like in the back end, the recursion used stack, correct, to keep all of these results, right, until it find the base one, correct?
yes.
But is it efficient? Imagine if your stack grows very, very big. It's mean that the memory wise, it's like extremely inefficient.
Mhm.
That's like, is it, do I understand this correct, I guess?
Yes, yes. So I said I didn't want to go to the cons of recursion until like we did examples. So yeah,
Oh,
that's like one
sorry.
of the yeah. But yeah, you covered it. So that's like one of the cons of recursion. So I said it can be slow, it uses a lot of memory and can sometimes be hard to understand. So these are like basic cons. So as you said, if we go back to this slide where we have this, so we have three function deep calls. So this string A calls string B and string B calls string C. So we need to keep track of three states. So when we are at A, we need to know that okay, we have hello, but we need to know what B's return is. And then when we get to B, we need to know what C's return is. So that's why we need these three stacks. So we need three stacks. So if we have, for example, sum with say, when we are calling sum with 10, so we probably have like 10 items, like we'll have like 10 items in the stack, right? And from her question, she said, is it efficient? So it gets to a point where we have like, if we have like a large number, it becomes inefficient because we need to have like a lot of memory. We need to store a lot of things in memory, right? And that will be inefficient. Even like sometimes we can not have enough memory that we cannot add any more items to the stack and then we get an error. So yes, this is one of the limitations of recursion.
Thank you. Thank you so much.
Yeah, you're welcome. So going back to this question where we need to implement power raised, like the raised power using recursion, right? So we have so we are trying to find the recurrence relation and we are trying to find a base condition. So first we are trying to find the recurrence relation. So we have 6 times 6. So basically we have this 6 times, right? Up to like 6 times, 7 times basically. So that means we are repeating something. So there's a recurrence relation, and the recurrence relation is multiplying the value, which is x, by itself. So we just keep multiplying the value, and we stop at the point where so the base condition is the count, right, of 3. So if we have 3, we need to stop after the third time. If it's 7, we need to stop after the 7th time. So let's see if we can write the function for this. So basically, first we write the recurrence relation, and then we write the base condition. So we have x and we have n, right? So we just need to return x times power of x and n minus 1. So what this does is we are returning. So if we have 5, we are doing 5 times, so if you have 5 raised to power 3, we have 5 times 5 raised to power 2, raised to power 2, right? And then, okay, let me even write this out down so that it's easier to understand. So as we said, if we have 5 raised to power 3, right, we have 5 times 5 times 5, right? And this is the same thing as saying 5 times 5 raised to power 2, right? So we have 5 raised to power 3 is the same as 5 times 5 raised to power 2, and it's also the same as 5 times 5 raised to power 1 as we have here, right? So this is the recurrence relation. So the recurrence relation is that we are multiplying 5 by, right, multiplying 5 by, so what we do is just multiply 5 and then we subtract 1 from what we are using to what we are raising the power to. So that's basically what we have here, x times x raised to power n minus 1. So this is basically what we are doing. But how it stops, how do we stop? How do we know when to stop? So we stop when our n is 1. So if n is 1, then we know that we can stop and then return x. So at this point, we know that we don't need to keep going, because if we do, then we would just keep multiplying 5 infinitely. So this would give us what we need, basically, right? I don't know if there are any more. Okay, yeah, I can see more questions.
No,
Okay,
it's not a question. I'm just trying to clarify what question she was asking.
Okay, cool. So yeah, I think this is basically it. I don't know if there's any more question. Let's try to run this. So if we say power and say 5 raised to power 3.
Someone asked a question and they said, why are we using -1? By the way, Zen, do you want to clarify your question more?
Can I answer the question?
Yeah.
Do you want to ask or answer the question?
She wants to
answer the last question. Answer the last question. Am I free to?
Yes.
Okay, yes.
Okay, Rofeat Olusanya. Why we are using -1 in this specific example is because of the 5 raised to power 3. He explained that 5 raised to power 3 is the same thing as 5 times 5 raised to power 2, which is equal to the same thing as 5 times 5 raised to power 1. So we're using -1 in the sense that, like, power x, that's 5, n, that's raised to power 3. So return x times 5 raised to power n minus 1, that's n 3 minus 1, that's 5 times. I don't know if I'm clear. This example just suits this particular example that he gave. Oh yeah, I love that. Thank you, bye.
All right, great. Thank you a lot. So who help answer?
Sorry, James here.
Yeah.
Yeah.
Thanks,
Yes,
Ibele, for that.
Thank you.
Zen, okay, you can go on.
Sorry, was someone else saying something?
Yeah, Zen was saying something. Zen, we
Yeah,
can hear you.
Actually, Ekene has already answered my function.
Okay.
I was just asking, returning the function.
Yeah, sorry, can you hear me?
Yeah, we can hear you.
Yeah, so I was just asking, like for example, where you returned x times power of whatever, whereby you are like calling the function itself in the return statement. So that's what I was asking about. You guys explained it.
Okay, great. So I'm trying to run this. Something. Okay, so we have our answer, right, which is 125. And someone asked a very brilliant question that this would not work when we have negative values for n. So for example, if you have 5 raised to power minus 3, right? So this will not work. Why? Because it will keep running forever because we'll not hit the base condition, right? Because we are subtracting 1. So when we subtract 1, we'd have minus 4. And then we'll keep going -5, -6, and it's like run forever. Actually, let's just try it and see. So if we call 5 raised to power minus 3, we get this error. Maximum call stack is exceeded. Same with what Zofia, I think, talked about, like memory-wise, it's not efficient because we called this power just kept calling itself multiple times. We didn't hit the base condition. So that's why you see that the base condition is important, right? So how do we solve this problem? We also need to find a way in which like we need to find how we can get the recurrence relation. We need to find a way we can get the recurrence relation. So then we now have to find out, okay, how do we get the recurrence relation? So 5 raised to power minus 3, right, is the same as, I think, 1/5 raised to power 3, right? And then we can now do this the normal way, right? So what we can do is we can have something to check that, okay, if n is less than 1, if n is less than 1, actually there's another case in which it won't work that we'll try to solve. So if n is less than 1, we want our x to be equal to 1/x, right? So which is this. So when we have this, we can now say 1/5 raised to power 3 is the same as 1/5 times 1/5 raised to power 2. And we have the same recurrence relation as we had previously. So let's try this and see if it works. Clean this off. Okay, we still have maximum call stack exceeded. So let's find out why we have maximum call stack exceeded. We have the maximum call stack exceeded because we didn't change n back to. So when we have this, when we write 1/5, then we now change x from my negative number to the positive number. So we also need to change n to -1 times n, right? So if we have -3 minus 1 times -3 will become 3, and then we can now like solve it the normal way. Let's see if this works. Actually, no, it doesn't work. Okay, so the good thing about, so something about what's it called?
I think we never get to our base. If our n is always less than 1, it's entering this loop, and then we're never entering our base.
Sorry, what did you say?
I think in our thing, we are never enter into our base case. That's why it keeps doing something.
Yes, and then so I would show you a way to find out, and then a way in which we can see the call stack and how it works. So would add something called a breakpoint, and then I would call this function with a breakpoint, and then we can see how the call stack gets how we can basically see the call stack. So let me run this. So here we see the call stack let me try to make this bigger. Okay, I think it can't get bigger. So what we can see here is we have power being, so this is the stack, right? This is basically the stack that we're concerned about. So we see that on line 17, we have the first call, which is here. So line 17 calls power on line 7. So it calls here, right? We have this. And at this point, we can always get the values of everything here. So here we see that n is -3, we see that x is 5, right? And then we can go to the next point in the stack where we have, so this is the second port, this is the second call, and we see like we have 3 items now on the stack, right? So on the second call, we have x being 0.2, which is 1 of 5, and n being 2, right? Then we go again to the next point in the stack, and we have x still being 0.2 and n being 1. So we see that I think there's an issue here because it shouldn't still be, or should it be? I think it should be 1 over 5.
Actually correct,
it's supposed to be.
the
Sorry?
answer you got was correct. There's 0.008 because it's 1 divided by 5 raised to the power 3. So it was correct.
Okay. Yes, actually, okay, cool. So we have this the second time, which is 0.2, and then the third time. Okay, so that's basically the end. Let me try with a bigger number so we can see the stack more. Okay, so the first time we have -5 and 5. Second time we have so we changed, because we had this call, we changed it to 4, and we changed it to 4, and then we did 1 over 5, which is 0.2. So if we keep calling this, right, we are going to have like a lot of items on the stack. So this is the stack that we have. I'm trying to expand this, but it seems I can't. So we can like click on every point to see what we have, like what the values are at each point of the stack. So this is the call stack I was explaining about, and like you need to understand this because, like, as someone said, if we have like a large number, say 100, we'll have a lot of items on this stack, and then depending on the machine or the kind of either machine or PC you are using, right? We'll get to a point where, or actually the language you are using, you can get to a point where you can no longer add any items to your stack, and then we have an error being thrown, right? A stack overflow error or a range error, depending on the language that we're using. Yeah, and I said there's one more condition that we need to fill. So if we have, so we can also have a situation where we have 5 raised to the power 0, right? So if we have 5 raised to the power, okay, I think did somebody say that in the chat? Yes. So if we have 5 raised to the power 0, that's the condition I said we were going to deal with later. So if we have 5 raised to the power 0, it won't hit this case, and it's yeah, it is not less than 1 and it's not equal to 0. So basically we can make it easier to understand by saying if n is equal to 0, then return 1, right? So with this, right, is basically the same as saying let me do the analogy again. So if we have 5 raised to the power 3, 5 raised to the power 3 is the same as 5 raised to the power 3 is the same as 5 times 5 raised to the power 2, right? Which is the same as 5 times 5, 5 times 5 times 5 raised to the power 1, right? So this is where we stopped before, but we can still go one step further and say, which is also the same as 5 times 5 times 5 times 5 raised to the power 0. right? So this is where we now want to stop, because we already know that 5 raised to power 0, anything raised to power 0 is 1. So we still have like the same thing, right? So that's why we have it this way. I don't know if there's any other question. Yeah, thanks, Richard. Okay, someone is saying we should try with a positive number. So yeah, it works with a positive number. You should probably check your code. So I don't know if there's any other questions. Okay,
Any
no
other
other.
person has any question?
Okay, so let's just treat the cons and then we'll end. So first, it can be slow. I would maybe touch a bit on how it can be slow before I end, since there are no questions. Now it uses more memory. So as we saw the call stack there, like as we saw in like when I showed the call stack, we can get to a point where like we use a lot of memory, right? And yeah, so that's another con. And then sometimes it's hard to understand. Yeah, sometimes actually recursion is hard to understand, most like the first time. I remember like the first time I saw recursion, I was so confused, like what's going on here, right? It took me a long time to actually get like even like the most simple cases of recursion. And then like the more you keep working with recursion, like the more you understand it. So that's it. And then so how can recursion be slow? Let's take another question. Let me see. The Fibonacci
Please, I have a
question.
question.
Okay, there's another question. Yes, yes.
Yeah. It's not really related to recursion, but it is. I know anytime we have these classes, we either taught recursion or there's something we used to do, like we put something inside a bracket and we'll be asked to pull out the second number or the second item. I think it's a list or so. Is it the same as recursion?
Okay, I've not been in these classes, so I don't know where.
Ebele, I don't get what you mean. Can you repeat it again?
Okay, I said this recursion is teaching us like how to create a code for repetitive function, something like that. There's some other thing that used to be taught in classes like this, where they'll be put something inside a bracket that is the bracket is not designed. It's like a straight bracket. It's not this one here. The bracket is like square-ish, and then we'll put a list of items, and they'll be told to bring out maybe the third item or the first item or something like that. Is it related to recursion too?
No, not really. This is like working with lists or arrays. This one you're trying to assess, what is in that list. So you're trying to probably use the position or something to assess the list or something. Yeah, it's not.
It's not related. Okay.
Yeah.
Trying to piece it in my head. Thanks.
No worries. Okay. All right, Ekene, you have like 5 minutes more.
Oh, so I'll probably not be able to explain how it can be slow. But then if you have like a Fibonacci sequence and you're trying to solve it with recursion, right? Most times, or it's actually easy to write recursions in a way that will be slow, because sometimes you might tend to do like work multiple times, right? So for example, if you have, okay, so this example doesn't have such cases, but if we have a case where we solve, so we can have a case where you solve one thing multiple times. So for example, because we don't have time, so we might not be able, I won't be able to cover the Fibonacci sequence, but if you guys have time, you can go through what's like how the Fibonacci sequence works, and you can try to like solve it with recursion. And then you've most probably find out that it's slower when you use recursion. And the reason is because you do the same thing multiple times. So I think that's basically it. Yeah, that's all I have. Thank you, everyone.
Thanks so much, Ekene. That was really awesome. I think people have been able to at least grasp the understanding of, recursion. Either it's a refresher course to you, trying to, refresh your brain on what recursion is. If you still have any other question, feel free to drop it on the chat or something. Ekene can always get to it. So, but for the meantime, time is always our problem. So I think, okay, somebody's just, explaining. So time is always our problem. And for the next 1 hour, we want to go into breakout rooms. He has touched on recursion. He has explained and he has done an excellent job of using examples to explain. He has shown questions. So what we want you to do right now is you're going into these breakout rooms. You come up yourself. So you are to solve this question with other people in that room. So you'll be given the question. There is a facilitator that will guide you around, providing solution to that problem, but you are the one doing the job. So you and every other person there. And I always encourage people to speak up. Please just turn on your mic. If you're comfortable, turn on your video, talk, and learn from other people while other people learn from you. He mentioned something like Fibonacci series or some, so you would have, I think so we have like 3 breakout rooms right now. Is there a way to connect to the instructor? Yeah, Ekene, they want to connect with you. So answer the chat. So while he's doing that, we have breakout rooms right now. I've created the rooms. So what you just do is you can assign yourself to the room. So we have 3 breakout rooms right now. We have like 2 beginner breakout room. When I mean beginner, I mean you are just like, starting out when it comes to this algorithm and data structures thing. You are just kind of new. You are very maybe you are still solving easy questions on lead code or Akarank, that kind of thing. So that's what we group as beginner can. And for intermediate, you are very comfortable with solving medium questions or maybe add questions on lead code. So feel free to join the intermediate room. So I'm going to open the rooms right now. You will see the rooms pop up on your screen or something. So you choose the room you want to go to. You choose the room you want to go to, whether you want to, for the beginner room, you can just go to any of the room. I can reshuffle later. But for intermediate room, like I said, make sure you're comfortable with solving at least medium question, because they are going to be solving medium to hard questions in the room and you don't want to, be confused. Help yourself. But if you like, you want to challenge yourself, it's totally fine. So that's what we're going to be doing for the next 1 hour. There are questions you'll be given there when you get to the room and you are going to solve it right now. So Ekene did a good job of, explaining through a question. He explained through the question, you didn't solve it, even though you're following, which was good. But right now you have to solve it. You have to solve it with other people. Think about it yourself, come up with the solution yourself. Recursion problems are not so easy. You have to find out the, recurrence, just like he said, and you have to figure out the base condition. So that's what you're going to do yourself this time around. So I've opened the breakout rooms and feel free to go into them. And while I stop the recording, for those that will be listening to recording, I have to pause the recording right now. We don't record breakout rooms so that people can be comfortable to talk. And if you want to join the breakout room, come to our session next time. Resume recording. So
this meeting is being recorded.
For those that will be listening to the recording, we're just coming back from breakout room. And like I said, if you want to experience what the breakout room is like, come and join the session. It's fun and that's all I can tell you. So I'm going to share my screen. But while I'm doing that, how is everyone doing now that you're back from the breakout room? Do you feel like we have drained you? Or do you feel like you enjoyed the session? How was that? I want to hear from you guys.
I think the session was really informative.
No.
I've already tried to solve Fibonacci once and I gave up. So Now I know how to solve it.
That's cool.
I think the total room is quite tasking.
What'd you say?
Quite tasking because
Oh. Okay, so I've dropped the feedback form. There's a feedback link. I dropped it on the chat. So please, give us your feedback. Tell us what we can improve aside for more time, because I mean, we need to always go back. Today is Saturday again,
We're actually about to ask for 5 more minutes.
Nah. Nigeria is playing football today. It's Salah day. We need to go and eat meat. So, anyways, if you actually feel like you need more explanation or something, you can reach out to your facilitators on Slack. I can drop the Slack channel and Slack link, so you can join our Slack. Oh no. Okay, hold on. I've not signed in. What? I'm coming. Just let me get a sign. Okay, yeah. So you can join the Slack, this thing, and then join the Slack channel. Someone wants to ask a question. Kingsley, you can ask your question.
Okay. So like I said earlier on, this is my first time joining the meeting. So I would like to know how often it happens, how often you.
Oh, that's a good question. Normally it used to be every 2 weeks, but things happen, life happens, and we have to always, but we try to ensure that we have at least one session every month. So sometimes it can be every 2 weeks, but life just happens. Plus it's holiday period and people are kind of traveling up. Don't mind me. But yeah, we try at least once a month. So, but anytime we have a session, we would always put it on the Slack and say, okay, this is the next session coming up, so date, RSVP. So you would at least get a notification. Even if that's the only reason why you want to join Slack, you can do that. So we have a Slack workspace for male codes, but it's not just for women, And then there is a Slack channel called algorithm and data structures. So when you join the Slack workspace, you can just search for the channel. I can put it on the generals so that you can always just click on it and join that channel. So that's where we put all updates as regards this series. And if you want to reach out to your facilitator again or ask any question, please feel free to ask it on that channel. So for those that could not, we are sorry for the time. Actually, time was limited for the breakout rooms, but I just hope you at least learned one thing or two. And if you want to learn more, maybe you have solving a question, you have issues with it, just reach out just send a message on the channel and someone will respond to you or something.
Okay, so I'm sorry again. The second question I have is that you made mention of facilitator. Are we assigned facilitators or we can meet any particular one whenever we have a question?
Yes, who was the person, what in the breakout room was your facilitator? You can just search for them on the Slack and just message them.
Okay.
Yeah. So that's it for today. Thanks everyone for joining again. We did it. Yay. And thanks for another awesome session. I also dropped the GitHub link on the chat. So we have a GitHub repository where we keep track of the session. So you can even check more on previous sessions in case if you missed anything, like maybe you feel like you need to learn more about tags, strings, you can check more on it on the GitHub page. And like I always said, please send us a PR of your solutions. So that's another thing. We would merge it. We have backlogs of PRs right now that needs to merge, but we would always merge them. We would also give you comments on what you need to do to make your solution better if there's any issue. So yeah, that's all for me. If you have any question, let me know. If you don't have any question, feel free to drop, and we hope to see you again in our next session.
Thank you
very much. Thank you.
Thank you, Hope.
Thank you.
Bye-bye. Thank you so much.
Yeah, for those celebrating Salah, peace Salah. For those celebrating.